Earlier in our discussion of the kinetic theory of gases, the topic, we had discussed about the ideal gas and the real gas and the equations concerned with them. And also, we had started off with a few gas laws. We had discussed about the Boyle's law and the Charles law. Now, we will be continuing with the rest of the laws, beginning with the Gay-Lussac's law of pressure. So let me just write that down for you. This is the third one in our discussion. So this is Gay-Lussac's law of pressure. What does it state? Well, it states that the pressure is directly proportional to the temperature for a given volume when the volume remains constant. Now, from that, what we get is that the ratio of the pressure upon temperature is a constant. That's it. And what follows is the graphical discussion where we take the pressure by temperature on one side and the pressure onto the other side, and this shall remain constant for a given volume. Also, we have the variation of the reciprocal of temperature with respect to the given pressure, and that varies uh, inversely and asymptotic nature towards both the axis. And finally, we top it up with the temperature versus the pressure, and for that the slope is a linear one, varies linearly. Now from this, what we also obtain is that the pressure ratio of the pressure and temperature remaining constant at the absolute temperature, we will have a certain pressure, let that be P naught, while T naught is the absolute temperature. And so the pressure will be related to that pressure corresponding to the absolute temperature like this, that is P is equal to P naught multiplied with T upon T naught, and that will equate to P naught. That temperature that we have T, it will be related to the absolute value, which is absolute value is obviously 273, that lies in the denominator, and at the top for that temperature we have 273 plus some value of T, and this equates to P naught, and that bracketed term is 1 plus T by 273. Now this looks pretty familiar, as in case of Charles' law we had obtained the expression which which gave the value of 1 by 273 as the volume coefficient of gas. Now we have the pressure coefficient of gas over here, which is the same obviously. Now we can represent that as gamma p. The values in both the cases remaining the same, that is 1 by 273, and that is equal to the difference in pressure per unit pressure per unit rise in temperature. So that is how we define the pressure coefficient of the gas. So that sums up the Gay-Lussac's law of pressure. Then we move over to the next law, which is the Dalton's law. Dalton's law of partial pressure. Now, any gaseous system that we consider, if it contains more than one gas or maybe a saturated vapor, they will exert some pressure by themselves. They will have individual pressures, and the total pressure as per Dalton's law, now the pressure that they may apply on a given container maybe in which they are placed, that is termed as the partial pressure. And this partial pressure from each of those gaseous system or saturated vapors maybe, they add up and they give the total pressure that acts on the container. So what it essentially states is that the total pressure that acts is equal to the sum of the partial pressure due to each of those saturated vapors or even gaseous systems uh, that is contained within the confined space. Now we can prove this if we consider that the total number, the total moles that is contained within the container, that will simply be equal to the individual moles, that is N1, N2, N3 likewise. So these are, N1 is the number of moles for the gas type 1 of the second type of gas. There are N2 moles of that. So and likewise it follows in the same pattern, and finally we have total N number of moles that is contained within that confined space, a given container maybe. And also for the individual gaseous systems, the partial pressure which will be having the common volume, because the container is the same, the gaseous system occupies the volume of the container in which it is placed, so the volume for each of those systems will be the same. Now, and so will be the temperature as well, because they will be exposed to a common temperature. So we have P1V to be the case of the first type of gas that we are considering, and for that the ideal gas equation will result in N1RT, R being the universal gas constant and T being the temperature, which is common for every gaseous system present in that confined space. So P2V is for the second gas, where we have N2RT, and it follows likewise. Now, so from this what we can get is P1 is equal to N1RT divided by V, and P2 is simply equal to N2RT divided by V, and again continues. So taking the sum of the left hand side terms, what we get is P1 plus P2 plus it goes on, and on the right hand side what we end up with is the N1 and N2 terms, they are left behind, taking the RT by V as the common term. And if we were to consider the entire system which is present within that confined space, that applies a resultant pressure on the walls of the system, and that will equate to nRT, where N is the total moles of the gases that is present, divided by the total volume, that is V, which is common for every bit. So on calculating or on equating the right hand sides, what we see is N is essentially equal to N1 plus N2, as we had predicted, as we had taken right from the very beginning. So that being the same, RT by V being the same, so these two equations on the right hand side, they are the same, so the left hand side terms must be same. So we end up with the total pressure being equal to the sum of the partial pressure present within that confinement. So that's the Dalton's law of partial pressure. Then the fifth law that we are to discuss is the Graham's law of diffusion. So let's write that down first. So this is the Graham's law of diffusion. Now what does diffusion mean? Well, diffusion as we know, not the S there, diffusion as we know it is the process of movement of gas from one region to another region where there is a difference in the concentration. So that is how we know the molecules diffuse from one point to the other where there is a difference in concentration. So how does that happen? Well, if we have supposedly we consider two different gases and they are at the same pressure and temperature, and they are in two chambers which are separated by a perforated membrane. Now it happens that both the gases, they tend to move from one chamber to the other through that membrane gradually, and the process is known as diffusion. So what Graham's law of diffusion tells us is that the rate at which the diffusion of the gases takes place, that rate is inversely proportional to the square root of the density of the gas considered. So what we have in terms of the equation is that if we are considering the rate, let's take the rate as a small r over here. So that rate is directly proportional, in fact inversely proportional to the square root of the density of the given gaseous system. Now, if we are considering the case what I just explained when I was talking about diffusion, that we have two gases which are separated by a perforated membrane, and they are maintained at the same temperature and pressure. So from that, what we get to know is that the rate of diffusion for the first gas will obviously be inversely proportional to its density, square root of its density. And if we take the rate of diffusion of the other gas, it will be inversely proportional to its density. So this is what we obtain from our discussion on Graham's law of diffusion. What it also tells us that the lighter the gas, the more quickly it will tend to get diffused. So the diffusion is greater for the lighter gas than the heavier one, that is with the greater density, because it's inversely proportional to the square root. And finally, to top it off, the last bit that we can consider is the Avogadro's law, a simple law which states that, now Avogadro, the names tells us that we are going to be concerned about the number of molecules or even the number of moles in this case. So what it states is that under the similar condition of temperature and pressure, for equal volumes of gases considered, there will be an equal number of molecules. So we have studied about the universal the ideal gas equation. PV is equal to nRT. So from that, what we get is PV by T is going to be equal to N times of R, and R being the same for each gas. If that is taken out of the equation, we are simply left with N. So now if we were to take the ratio over here, then what Avogadro's law tells us is that for P1, V1 and T1 being equal to any other gas which is maintained at equal temperature and pressure, and the volume, and with the volumes being same, they are bound to have the same number of molecules. It is quite evident from the ideal gas equation. So the number of moles being the same, the number of molecules will definitely end up being the same in this case. So that is what the Avogadro's law is all about. Now moving further into the topic, we shall be discussing the kinetic theory in its most raw form, that is the theory which leads to understand the behavior of the gases, and that can be studied by the motion of the molecules, and hence the name that we have, which carries the term kinetic, means it involves the motion, and it is the motion of the molecules that constitute the gaseous system, which leads us to explain the various behavior. The laws, the gas laws that we just studied, they can be easily explained by knowing the behavior that is obtained by considering the motion of the molecules that are present. Now, for that, we will have to stick to the basic postulates. So we'll be discussing that first. So what are the basic postulates of the kinetic theory of gas? Basic postulates of kinetic theory. Now, one of the first assumptions or postulates that we have to consider is that all the gases that we would be considering, they are obviously composed of molecules, and these molecules will be similar in a given gas, but will differ for other gases. Seems quite proper. Now, for the second case, what we need to consider is that the molecules are always in a random motion. Molecules that are present, that constitute the gaseous system, they are always in random motion, and this random motion may have the molecules involved, they may have velocities which will be ranging from 0 right up to infinity, and because it's random, we tend to explain it through this zigzag kind of motion, and this zigzag motion is what we usually term as the Brownian motion. And in the third case, we consider the size of the molecule to be negligible, as we had discussed previously that in case of ideal gases, the molecules must be point masses, so this will tend to point masses, if not exactly point masses, but they must tend to the point masses for uh, proper ideal behavior, and that's what we are assuming at this point. And they are obviously regarded to be perfectly elastic. The behavior will be perfectly elastic is what we assume at this negligible size. The fourth point tells us that the molecules collide with each other for sure, and the collisions will be instantaneous. The collisions that are involved will be instantaneous. And in between two consecutive collisions, they'll travel a path in straight line. We need not take them to be curved or anything, just like in that short diagram that I've shown you. So probably this is the first molecule which is colliding with the second molecule over there, and then it is moving over to the third molecule, maybe scattering or recoiling from that point onto the third molecule. Now as it moves from the second to the third molecule, the path, as you can see, is a straight line over there. So the collisions being instantaneous, the path that is taken between two successive collisions is a straight line, and that path is termed as the free path. Now, an average of all the observations that are taken into consideration lead to the mean free path. So the average of all the observed free paths is obviously termed as the mean free path. then we also consider that the collision between them is perfectly elastic, that we have taken up over here, because they are perfectly elastic bodies. So is the collision between them, and they do not exert any force of attraction or repulsion between them. They do not involve that. And there is obviously no change in the number of molecules per unit volume. That is, the number of molecules per unit volume, we take them in the centimeter scale, in the CGS scale, that is, per unit volume, is always a constant. So these are few postulates that we must consider, and what that will lead us to is studying the behavior, as I mentioned. And how do we do that? Well, we just obtain a few expressions from it, uh, which will lead us to a few more explanations, essentially the gas laws that we have just studied, and many more terms that are associated. So to begin with, we obtain the pressure that a gas possesses by using these postulates of the kinetic theory. So let's get started with that. So in order to obtain the pressure of a gas, what we first consider is that uh, the gas or the gaseous system is present within an enclosure of cubical in a cubical enclosure, that is, that we can see in the figure right in front of us. And that enclosure, each with the length of each side being L, and with that the gaseous system will tend to exert a certain force on each of the walls of that container, and the force per unit area is what we call as the thrust per unit area. That will constitute the pressure. So we wish to obtain that. We wish to obtain the force per unit area in the given case. Now we are considering a constant volume of the value V, which is equal to L cube, because the length of each side is L in that case. And they have been aligned with the axis, as you can see, the X, Y, and the Z axis. And with a molecule considered within that given volume, let's say we consider it over here, not on the wall, but it's a three-dimensional case, so we'll probably consider it in the middle. So let's assume the second one that I have just drawn, and that is moving with a certain speed in a certain given direction. That is probably moving with a velocity, let's say c1. C here does not really tell us about the velocity of light. It's c1 is something that we are considering for that given molecule. Now this c1 is equal to the square of it, obviously vectorially considered, is equal to the square of each of the rectangular components, which are u1, v1, and w1 squared. u1 squared plus v1 squared plus w1 squared, where, if you have guessed it right, u1, v1, and w1 are the components of its velocity in the x, y, and z directions respectively. So u1 along the x direction, v1 along the y direction, and w1 along the z direction. For now we will be considering only the x-axis, so for simplicity we are taking the component which is moving, which is along this direction, that is u1. Now that u1 will have, with the mass considered for the given molecule, that momentum will be mu1 as it moves from the left of your screen towards the right, and it strikes this particular surface that I've shaded just now, the ending surface on the x-axis. And as it strikes, being elastic in nature, the collision will be elastic and it will be rebounded and it will return along that same path, and it will be back with the same momentum as well. So the change in momentum that we expect will be the final minus the initial. We can take the final momentum to be because it is taking going to rebound in the negative direction of the x-axis, so the negative direction of x-axis will result in a momentum of minus mu1, and the initial momentum, this is the final momentum minus the initial momentum, which was mu1 that I had just written before giving the minus sign to it. So this is the change in momentum that it experiences, because from change in momentum we can determine the force or the thrust that acts, and as a result of that we can make assumption or calculate the thrust per unit area. Now the molecule is turned back by that face, and it tends to strike the other surface. So the change in momentum of the molecule in 1 second is going to be the change in momentum during one collision multiplied to the number of collisions per second. So it's not that it's going to take a unit second for first collision and the unit second for the second collision. There will be multiple number of collisions within a given second, because the molecules may be traveling at very great speeds. So what we say is that the change in momentum is going to be equal to the change in momentum for one collision, and that will be multiplied to number of collisions that are taking place per second. The molecule travels through a distance in that period, obviously, as it moves from one wall to the other and back to the first wall. In that, it has traveled through a distance of 2L. Now the time taken for at least two consecutive collisions, that is starting from one wall, let us say this wall, let me name those walls. I am naming the left wall along the x-axis as let us say B, and this right wall as A. So as it moves from one wall B to the other wall A, and then from A back to B, it has traveled through a distance of 2L, and it has traveled with a constant velocity along the x direction, which is u1. So the time taken between two successive collisions, remember it's going to be successive because we are having the first collision on the A wall and the next collision on the B wall. So between two successive collisions, that is going to be equal to the total distance upon the speed in which it travels, and so the number of collisions per second is going to be equal to 1 upon the time of the two successive collisions that we just obtained. And so this is going to be 1 upon 2L by u1, so it is going to end up with u1 by 2L. Now this is the number of collisions per unit time, and as we said, the change in momentum is the change in momentum for one collision, which is obviously minus 2 mu1. So this is the change in momentum of the molecule in 1 second that we are going to obtain. So the change in momentum is minus 2 mu1, which is the change in momentum in one collision, multiplied to the number of collisions per second. So that is equal to u1 by 2l, and so we end up with minus of m u1 squared upon l. The 2's cancel out and the u's get multiplied. Let's move over to the next page. Now, because this rate of change of momentum, as we just deduced, is taking in 1 second, that is unit time, so this is also the force acting on the molecule due to the wall. And the wall exerts a force of, that is, minus mu1 squared divided by L. And since action and reactions are equal and opposite, so the force on the wall due to the molecule will be the reaction force, and it will be equal and it will be opposite, so it will be mu1 squared upon L, but in the positive sense. Now the other molecules will also exert, this is a single molecule, now the other molecules will also start exerting the same kind of force. With their respective velocities, they will have a certain force. So F1, if we consider F1 as the total force that is exerted on A, on the wall A, by all the molecules, then what we end up with is F1 is equal to mu1 squared. Now the masses will be the same, the length of the container is the same, so along the x-axis, so only thing that differs is the respective velocities of the individual molecules concerned. So we are considering supposedly n number of molecules, so what we have is mun squared upon L as the last term. Now this is the x component, the u1 and u2 and up to un, these are the x components, and we have the net velocity for each case being c1, c2 and respectively up to cn. Now the pressure that acts on the wall is going to be the force or the thrust per unit area, and the area that is going to be there is L squared. So this is F1 upon L squared, and that will be equal to, if we take the L out of the case and the M out of the case as well, we have M upon L cube, and the rest of the terms, that is u1 squared, u2 squared, right up to un squared, remain within the bracket. And as we can see that L cube that we had discussed right from the very beginning is equal to V, so this is M upon V, where M is the mass of each molecule, which is the same for a given gas as per the postulate that we have considered for kinetic theory. Now these are the x components. Now if we assume the pressure in the y and the z components to be P2 and P3, will achieve similar expressions where we have M upon V, and the bracketed term will consist of, the bracket will consist of the terms V1 squared, V2 squared for the y-axis consideration, right up to Vn squared, and for the z-axis that we have taken as W1 squared, W2 squared, right up to Wn squared. So the total pressure or the mean pressure is going to be the sum of the pressure on each wall upon the three walls that are considered, so divided by 3. So what we are going to get is M upon 3V, if we are taking M by V as common for all of those cases, and for the U1 square, V1 square and W1 square terms being added, we get C1 squared, and likewise for the second terms we get the C2 squared, and finally up to Cn squared. So this is the the expression more or less for the pressure. And if we happen to multiply the n, and we cannot just do that, we have to divide that entire thing through n as well. So what we obtain is that we sneak in this n within that bracket. So instead of taking it over here, I am taking it right through the bracketed term which is there. I've just taken it there. Now this bracketed term, it gives me the mean of the square of all the velocities that we have, where if we see c, if we take it as the mean, that is c square is the mean supposedly, that is c1 squared, c2 squared, and right up to cn squared, and the mean of that we have c squared. Then we define the root mean square velocity, as c, which is equal to the root of the mean of the square of all the velocities. So that is the root mean square, or RMS velocity of the gas. And over here what we have, this is an extra thing that I've mentioned over here. Now over to this, what we get is m gets multiplied with the n term, and so mass of each molecule multiplied to the total number of molecules present is going to give me the total mass of the gas. M is equal to m times of n, and so what we have for pressure is that pressure is equal to m by 3v times of c squared. And as we know that m upon v is going to give me the density, which is given by rho, so the pressure is equal to 1/3 of the density multiplied with the square of the velocities, or the square of the root mean square velocity. Now the RMS velocity is also related to, from this equation that we have over here, from that what we also have, that the RMS the square of the RMS is equal to 3p over rho, or simply the root mean square velocity is going to be equal to the square root of 3p over rho. That's another expression for the root mean square velocity. Now if we are to consider the pressure in terms of the kinetic energy that is possessed by the molecules, so pressure is simply we can just make a few changes. What we do is we multiply a 2 and take the 3 out. If we have multiplied a 2, we must divide it by 2, and the 3 gone to the others, to the left side, we are just left with 1 by 2. 1 by 2 times of rho c squared from that expression at the top, the boxed expression, and that is equal to 2/3 of m upon v for rho times of c squared. Now mc, half of mc squared, now there's a half over here, half of mc squared is going to give me the kinetic energy term, so that is the kinetic energy, and 2/3 of it upon the volume, or it can be expressed as simply the kinetic energy per unit volume is expressed as well, in most cases we use the notation to be U, but here I'm taking it as E. This is the kinetic energy per unit volume, or the kinetic energy density, and that is related to the pressure as 2/3 of the kinetic energy per unit volume. So this is more or less the expressions that we associate with the pressure, as well as the uh, root mean square velocity, and there are also many more forms of this expression that we are going to discuss, but that will be discussed in the upcoming videos. Till then, thank you for watching.